Ladies and gentlemen, welcome back for a small part, welcome for a larger or the largest part. We are at the union session US1, we tend to say, but I would like to introduce something new, which I said already earlier. I think it's appropriate to say it us one, because it's ours. And I also repeat what I did before, and I kindly would like to request that you do what I do right now.
That's on the screen.
Thank you. Switch it off. It's a great pleasure and honor for me to announce one after the other 3 medal lectures, our main 3 medal lectures, union medal lectures. We had a ceremony which most of you didn't join, and we now have the lectures. And I would like to announce the first lecture by Jean-Pierre Bibring. Please, Jean-Pierre. You are there. Jean-Pierre Bibring will give now us the Cassini Lecture 2008. It's titled Mass History and Evolution Revisited by Ongoing Space Exploration. Dominique Cassini Medal Lecture 2008. Welcome.
Thank you very much. Mesdames, thank you, my friends which are in the room, all the colleagues of all the ages. I have said previously, it's almost trivial and stupid to say so, but it's really honored to be there and very moving. And of course, we are very proud too. And if I say so, it's because the pride really comes from the fact that I am capable today to present results, not my results, but the results of the team. And really, this team deserves to be presented because what we obtained during the past years is really, I think, enormous in a sense. So I'm very proud to be able to talk on behalf of this team, and I will focus, most of the team will present their own contribution during this meeting. I will focus on a very specific part, but the pride comes from the fact that actually with these present Mars missions we have now, not only the Mars Express one, but all of them, plus the one we are building, really we are touching questions that really are revisiting the entire understanding we have of basic things like what planets are, how they form, how they evolve, why the Earth is so different from all the rest of the world. And in particular, I will focus on one of the questions, do we know much better than we did in the past whether or not life could emerge other than on the Earth? So my focus will be really there, and what I would like to stress is that this question of whether or not there is habitable worlds elsewhere has always remained a non-scientific issue. It was up to very recently dreams to understand things, but there was just no capabilities on the observational side to put any sort of good answer there. And I think that the excitement comes from the fact that really, and I will try to sort of convince you on that, with the present Mars missions and the upcoming one that we're building, we are putting this question, whether or not there are habitable worlds somewhere else, in the scientific era. For the first time, we are really capable of putting some processes to this question and approaches as we would do for any other question. It's not only imagination, it's really interpretation. So very rapidly, to understand where we are, we have to go through where we were. And of course, we have to start 50 years ago up to the pre-space era. What did we know at that time about the planets? And the only thing I want to stress here is that up to the late 60s, there was essentially no measurement that could rule out the fact that life existed somewhere else, in particular on Mars. There was no possibility to know that. And what we knew that there were seasons on Mars because we had these polar caps, and just because the observation, telescopic observation on Mars over the years showed that there were changes in colors that could be interpreted in terms of seasonal variation of the vegetation itself. And when I said interpreted, it was really imagination more than anything else, because we didn't have the resolution that, again, there was nothing against that. So the key point at the beginning of that was up to the late 60s, nothing could rule out that really. At the same time, we were here addressing the question whether or not there is life elsewhere. There could be people elsewhere asking the same question. And of course, we know now that we are the only one, at least in the solar system, addressing the question now. And on Mars, no one today, at least, addressed the question. So what happened among these past 30, 40 years is that really, with the space era, we have entirely changed our world and our view of the planetary world, that I will just summarize out of that. Because we have to remember that 50 years ago, we couldn't even know for sure that all the sun and all the planets were born at the same time from the same material. That's been demonstrated essentially by the 860s, by the general samples. We know that we have huge commonalities in our origin, which was not trivial at the beginning, really. That really we share the same origin in terms of dates, location in the galaxy, and essentially the material. And of course, by contrast with that, we have, as I said, dialectic contrast, which is amazing, that when we see the bodies 50 years after we understood they were born 4.5 billion years ago from the same material, there is not really two single bodies looking the same. And in the textbook, all the people trying to summarize that like families of bodies, whatever, that just translate our ignorance of what it is. The real question is, why are they so specific? What are the drivers of the planetary evolution that from a given point has given this huge diversity here? And of course, the least is not to understand why the Earth has the capability for life to emerge, and more than that, to maintain and sustain the condition for evolving, for this life to evolve. It happens that, to understand that, essentially Mars is absolutely unique to give us clues. That's not the only body. That is very unique, and essentially I have not time to discuss the reason why, but it's schematically showed here by the size. The size of Mars is just what we need to have Mars a very specific role in understanding the planetary evolution. It's large enough to have undergone a lot of tectonic effects, much more than the Moon, as you know. But it's not too big not to have reset all the things. And so we have kept the memory of essentially all the steps that put the history of Mars together. And when you see that, that's absolutely critical, and we just start to understand the reason why. And of course, the real question we have now is, just because we know that essentially we might have had the same starting point, and now we have a diversion in the evolution, these diversions happen before and after, if I can say so, life happened on Mars. In other words, did Mars had time to harbor the key ingredients for life to merge there, and then possibly to have that stopped? But did we have that? And this question now, as I will say, is progressing a lot, and we start to have an understanding of that. And the last point I want to make in this introduction is that it's absolutely remarkable that the European community, essentially from Mars Express, but not only from the Mars Express mission, is playing really a critical role, and in the future with the ExoMars and MSR program that I'm going to touch by the end, to contribute to this really major quest. Do we know whether or not life could start elsewhere than on the Earth in the solar system? Of course, that requires that the politics follow, and as I will also touch that, the ministerial by the end of the ministerial by the end of this year will have a key role there, trying to maintain or sustain our programs. So, very rapidly, what we know for years now is that indeed Mars has an atmosphere, very tenuous, 2 orders magnitude less than that on the Earth, sufficiently low for liquid water not to be stable. CO2 dominates, but the key point here, and there was a Venus session this afternoon, very strikingly, Mars and Venus has the same amounts of gases, essentially, CO2 dominating, N2 over CO2 3%, but we have 4 orders of magnitudes less on Mars than on Venus. So on Mars, essentially, we have a huge escape of the gases that maintain the ratios that decrease the total abundance. And that's, of course, in big contrast with the Earth, in which only CO2 disappears, but N2 is still there. And so, of course, that tells us something which has already been underestimated, that the process by which the atmospheres of Mars and the Earth evolved is entirely different. And in particular, all the search the people had that CO2 would be on Mars also trapped as it is on the Earth in form of carbonates, that would demonstrate that we had on Mars also oceans in which everything could have been trapped. That's probably not true, because if that would be the case, then N2 should still be there, which is not the case on Mars. What do we know also? We know that Mars has preserved a huge diversity of the structures. When we see the structures, and these are the splendid molar views of the topography, we have a lot of diversity here, similar to what we might even have on the Earth, except that that's preserved for more than 4 billion years. 2 examples. This one is an enlargement of this size here. If I do not put a caption here, you wouldn't know whether this image comes from the Moon, on asteroids, on Mars. It's from Mars. And that tells us something absolutely critical here, that Mars obvious. We knew that, of course, also suffered this heavy bombardment, but half of Mars has kept the record of these times. And of course, the question is, we know that the structures are there, and the structures are there from the more than 4 billion years. The question is, do the alteration has modified the material itself, or do we have the capability, if we land there, to still have the material as it was 4 billion years ago? That's a question that was not addressed prior to Mars Express, and that Mars Express has essentially solved. And if this is a map of this crust here in colors, with Omega, we have essentially been able to measure the composition of that. And all what you see in the back here with the colors here tells you only this thing, that all the crust here, the heavily cratered crust that you are here, which again dates more than 4 billion years ago, has kept its composition in terms of what we call the mafic material, pyroxene, olivines, feldspar, whatever it is. It's still there. It's essentially non-altered. In other words, to this question, whether or not we do have still material dating of that time and altered, the answer is yes. And the conclusion of that you will see is absolutely key, is that if you want to find on Mars terrains which are contemporary to the time life emerged on the Earth, they are still there. There are places in which, if you land, you will see the material as it was 4 billion years ago. And that's, of course, not trivial. And that's been demonstrated a few years ago by our instruments. I don't know what that... Next thing, of course, is that, as you know, you have volcanoes on Mars, and volcanoes on Mars, as compared to the Earth one, are very, very small numbers of them and are huge. I'm not going to discuss that in length. Everyone knows that. This is 1,000 kilometers large. It's a huge volcano. It's the largest one, but they are essentially all the same size. And of course, the question is, when did this volcanic activity stop? And the recent HRSC, which is the German high-resolution camera on Mars Express, did a very huge work trying to measure in all the places, including the caldera here, by just counting the craters, just in quote mark, counting the craters and the diameter of the craters, having an idea of when, for the first time, for the last time, the volcanic activity ceased. And when you do that, these are the colors that show that for this volcano, which is the Olympus Mons, essentially all what we see is that it stopped between 100 and a few hundred million years. If we go to the other ones, like this one, for example, we have volcanic episodes from more than 1 billion years, giga years, down to a few tenths of million years, and the same for all the others. In other words, most volcanoes on Mars show that they have been active over almost the entire history of Mars, but there has been only very few volcanic activities because you still see the ancient outflows which have not been erupted or covered by the recent ones. So actually the volcanic activity were very limited in numbers, but they happen only a very few numbers of times and not very heavy numbers of times, and that's important. In other words, most of the volcanic activity on Mars is not really in the volcanoes, and that's been understood very recently. The measured volcanic activity on Mars was the building of this huge stack that we call Tarsis here, more than 10 kilometers in size and several thousand kilometers in wide here. There has been a huge volcanic activity there, and also you have all the northern plains which have been filled, exactly as the mare on the moon has been filled by the same sort of process. And the important thing is that because there is no crater there, it means that these happened after the heavy bombardment ceased. That's one thing of importance. And the second, which has been shown by the US NGS instrument on NGS, is that essentially all the colors show where you still have remnant magnetization on Mars. I'm not going to discuss that in length, but what is important to understand is that on Mars now you don't have any dynamo operating because the dynamo stopped very early in the process. But at the time the crust cooled, when it's solidified, there was a dynamo, and that's why the crust has these remnant magnetizations trapped and stored in there. But when Tarsis was built and where the northern plains were filled, they crystallized in an environment in which you didn't have any dynamo. If not, you would have remnant magnetization here too. So what we understand, and that's also seen here, that essentially these very early volcanic activity, let's say 3.8, 3.9 billion years ago, happened after the bombardment ceased and after the dynamo dropped. And of course, if I put an emphasis here, that you will see that this is one of the key differences between the Earth and Mars that explain where we are now. So, again, to summarize that, the volcanic activity by the volcano is not necessarily the major volcanic activity. The big volcanic activity was the very early building of Tarsis and filling of the northern plains, but that happened after the heavy bombardment ceased and after the dynamo of Mars dropped. There is many other things. I have no time to discuss that. We have been able to measure the composition of both the crust and the volcanic outflows, just to say that actually we have shown that the crust solidified out of a very fully melted magma, while the volcanoes were only partially, the magma out of which it fell was only partially melted because we have much enriched calcium. It's not very important for the story I'm going to tell now. The last point I want to stress, of course, is that sort of images which have been shown for the Viking times, which, when you see them, if you forget about the craters here, you don't know where it comes from, you could see it's on the Earth. It has really, it really resembles any sort of trivial activity. And when the people saw that, they said, obviously, in the old times, you had water available there because you had systematic fluvial activity there. Of course, and I will go back to that, and this is critical, I think, this doesn't mean necessarily that the water at that time was stable at the surface. In other words, it's not because you see that you had a sustained process with water getting that and then rain and water as well on the Earth. That does not demonstrate that water was stable. It just shows that at a given time you had water, liquid water, on the surface that could make the structures. You have the structures. It doesn't tell more than that. It doesn't actually even tell you that it was water. It's afterward that you understood it. It's probably water. It doesn't even tell you that it was water. And there is many of these, and the summer and the winter on the same places show you that actually there is some water on Mars, but the water is very tiny. Now we have a few ppm only, of water precipitable on Mars, so you can't ski there, but there is some water, and the reason why it's there and not liquid is just because the pressure and not the temperature. The pressure is not sufficient to maintain the water above the triple point, so it's either ice or gas, but never liquid. And of course the question is, what was in the past? And for a long time, Ames in particular, NASA Ames, put that sort of image here, saying, well, that's what it is now, that's what it was in the past. If we were capable of being a picture of Mars 4 billion years ago, that would have been Mars. And of course, resembling the two, it tells you something very important. That's an enlargement of that. And actually, if you take all the landers on Mars, they always landed in the blue of this map for an obvious reason. Because, again, the conviction was that in the old times you had water available. The basic idea behind that, I say that you had water available exactly as you had on the Earth. There is a reason that could explain why today it's no longer the case, just because Mars being smaller, it could not entertain the internal activity, so you had a slow decrease of the internal activity, so no replacement of the gases, and so the water would be trapped into permafrost. And of course, if that's the case, the CO2 would have been trapped in the water in form of the carbonate. So the idea was that if that was the case, to be sure of that, you should have permafrost and you should have carbonate. And if you find that, then the carbonates will tell you where the water was, and exactly as on the Earth in chalk you have fossils, that's where you would like to find the fossils. And so that's what essentially people did, and the result is that we never were capable of finding neither permafrost or carbonate as long bodies standing on things. And it's not by lack of instrument, because really I can say that the instrument that we put in place from the past 4 years are really, were not dedicated, but almost dedicated to that. And the net result is that there is permafrost very close to the poles, but that's normal. At lower latitudes, you can't find them, and carbonates are the same. So you have to modify your way of thinking of the climate of Mars. And what I say here, that really we can speak or quote an astrobiological failure of all the missions, and I will try to explain to you where and why we think we have a way to understand why we failed finding that and why we might in the future not fail. So the revisiting of all this exercise was made possible essentially by two things. And one is stressed here, that up to now, essentially, the imaging was the key thing to understand the planetary bodies. And of course, that's great, because without images, you can't understand anything. You have a lot of processes behind that. But the problem with the processes that you understand through the imaging is that you are too biased by the fact that you want to have an analog with the Earth. As I said, for the fluvial activity, for example, or many others. When you see something, you understand that in terms of the analogy with the Earth. And then that's maybe very misleading. The only possibility to try to oppose to that is to couple the structures and geomorphology to the composition. And the possibility to couple the composition to what you see is really what happened recently. And that's really why I think we're in a position to revisit the entire history. And I will essentially explain you that very trivially by one or two examples. First example is this example from the 19th century, where we understood that if Mars is red, it's not, I mean, Mars, was plenty of dead Mars blood, right, for 2,000 years, until the 19th century, where finally red was assimilated to rust. And so the people said, if it's red, it's rust. If it's rust, it's water. If it's water, it's life. And these sort of things really covered the entire 2 centuries, and it was not trivial to... Actually, it's very interesting to see and to try to understand why red and rust we can understand. Rust and water, it's a little more complex. Why water and life so coupled? Only now we know why it's coupled. But in the 19th century, they didn't know it. And even in the 20th century, they didn't know why water was so important for life on the Earth, at least. And there are good reasons for that, in particular, given what the atmosphere, you have to shield the solar light, but that was not clear. So, first of all, is the first assumption right? Is it true that if Mars is red, it's because it's rust? In other words, is the red color coming from the oxidation of the ferrous into ferric oxide? That's the map I showed you of the mafic minerals in the crust, and of course there is a lot of black here. If it's black here, it's because we don't see the magmatic material out of which they were made, because this also is a magmatic origin here. So if you don't see them here, it's because you have had an alteration here. And the question is, what is this surface altered material? And when you make an optical images here, and you correlate the two, actually what is black here is what is red here. In other words, there is a correlation by the fact that when you do not see the pyroxenes, olivines, or whatever, it's because it's been altered in this reddish material. So there is a connection there. And what we did is try to understand what is the composition of that. They are better mapped, but that was the very first one, and that's why I like it. The colors here essentially refer to the abundance of the ferric oxides, actually what we call the alpha Fe2O3, the hematite. The wider here, the redder you have, because you have a huge amount of that here. And actually you have a one-to-one correlation between the fact that Mars is red and you have ferric oxide. So the first question is, yes, the fact that it's red implies that it's rust. The answer is red. But of course the next question is, that means that it's made, oxidized by the water. In other words, are the ferric oxide hydroxides? And this is something that we did for the past 2 years or 3 years, and I think it's maybe one of the most important things. And the idea is from the following. In the near-infrared where Omega works, there is something absolutely specific and important, that whether it's OH or H2O, you cannot hide it in the infrared. You can't, it's a very good spy. Infrared really delineate any piece of OH and H2O, whatever the state it is. It's very difficult to hide it. So either it's OH or H2O on the ground, whether it's hydrated in the rocks, absorbed, physically, chemically absorbed, you will see it. And so we could draw a map of all the places on Mars where there has been hydration. And that essentially, at that scale, the maps. All the colors here, as you will see, they give us a different composition, but essentially you do not have hydration anywhere else than here. And in particular, all these black areas here in which you have this red dust, it's not hydrated. The dust is not an hydrated dust. It's hematite, it's not goethite, essentially, for those of you who know a little of mineralogy. So, to be fast and quick, rust, yes. Water, no. Water is not responsible for Mars to be red. We have here an hydrous ferric oxide, and no more than that. So the very first thing we understood that water is likely not the ingredient that was responsible for reddening Mars. It was not trivial to understand that, because then you have to understand why is Mars red. And the answer is, essentially the oxidation comes from the interaction with the atmosphere. You have only a few ppb of H2O2 in the atmosphere. That's sufficient to oxidize, but it takes billions of years to do so, and only on a very, very shallow stuff, because it's on a sub-millimeter scale. You don't need to go deep, meter deep to know that. For example, if you see the rovers here, why do you see the rovers here? It's just because you have some gardening here that puts on the surface non-altered material, the same here. And the depth of that is only a sub-millimeter thing. So as soon as you just garden half a millimeter or so, you have the pristine material which has not been oxidized. Oxidation is a very, very tiny process. And if we go back in 2 or 3 billion years from now, Mars will be entirely red, because in 3 more billion years, we have time to oxidize the entire Earth's surface. That implies that Mars never underwent aqueous alteration process, and of course that's the key part of what I'm going to address now, and the answer is no. Ferric oxides are not the recorders of the water in the past, but Omega has shown that there is 2 other classes of hydrated minerals that are key to understand the history of this planet. And essentially, there are sulfates and phyllosilicates. I will be very brief. It's not a mineralogy lecture here, but I will explain to you why it's important and why we don't have carbonates. Again, the carbonate things, I have no time to cover that, is absolutely key because that's always been understood as the recorder of the fact that there has been ocean and the CO2 disappeared, just being trapped into carbonate. The fact that we don't see that, of course, is key. So then I have to go to the colors here, and essentially the colors are such that blue and green are the sulfates, and all the rest, which is spread over the entire planet, the yellow and red are what we call the phyllosilicates, which in the common language are just clays. So you have clays, hydrated clays, and sulfates, which is a salt. If you go to the sulfates, essentially the sulfates are located in one area on Mars, this one, close to this red thing, which is the Tarsis bulge that I showed you before. And you will see it's very important that the two are coupled. Tarsis is here, the sulfates are there. And actually, we propose that there is a coupling between the fact that we find the sulfates there and that Tarsis was built, and I will explain to that in a minute. If you take an enlargement of these, there is two places that we like to show in which we see these. This is Juventus in Valles Marineris. You have these places here, which is almost 3 kilometers in altitude. It's a big thing here, 2.5 kilometers in altitude, 50 kilometers wide. When we put our instrument there to know the composition, we have demonstrated that all these strata are made of gypsum, which is a calcium sulfate, CaHO4 with 2H2O. And kieserite is a monohydrated sulfate also of magnesium, very rare. That is important because kieserite, as soon as you put water there, kieserite is transformed. In other words, you had one time in which you made this mineral here, but it was not to sustain activity with water. Another place here, Chondrocasma, also in Valles Marineris. It's a splendid HRC image in which we didn't dare to cover that because we have shown that all the strata here, all around here, are actually sulfates also. So we'll later explain to you, if you are interested, why we have sulfates here, but actually there has been sulfate. Sulfate is a salt. You need water at a given time to get there, and it's when the water gets out that you are left with the sulfates. So sulfate doesn't tell you that water was, again, permanent, perennial. I remember that as soon as sulfates were important because that was the only and single mineral that NASA discovered as potentially made by water. When Opportunity in early March 2004 discovered that. And I remember Ed Whaler at that time, which is back to NASA actually, who said after this dramatic confirmation that water was present on Mars, the next step is to find a microbe there. And of course it's not true because sulfate doesn't tell you that there was sustained water in which life might have emerged. So sulfates are found in these things, and importantly, when you go to the composition of that, they require a very specific environment, very acidic. The other family is the phyllosilicates, but the phyllosilicates are found essentially in very small spots over the entire planet here, and I will show you just one place, Mars Valles, and you will understand why. Valles are these big outflows that we have on Mars, and they are interesting because these outflows have always been understood as the places from which water went here and then empty or fill these big oceans here. In particular, remember that Ares Vallis is the place where Pathfinder landed in 96, 97. It was launched in 96. And that the image of Pathfinder, they landed there, they analyzed the soil, and they couldn't find any droplet of water there. It's only ashes, volcanic ashes. So they had to demonstrate, and to understand why, putting their lander where they thought the ocean was, they couldn't find the trace of any ocean in the past. So we did the same here with Mars Valles, and I will very briefly explain to you what we did. On the right, you have an HRC image here with false color, and again, I don't like that false color here, because the blue, of course, tells you that water was there, and that's the reason why the people put blue there. When we put omega there, these are the real colors. There is no water there at all. There is no hydrated minerals, neither here or there. But all this white stuff here, we have shown that these white stuff here are filled with hydrated minerals, these famous phyllosilicates here. And the reason is that actually there has been big outflows that make these channels here, but it was transient processes, not sustained processes. And because they were too violent, they did not left the record of the water there, so the minerals that take time to be hydrated could not be hydrated, and essentially the hydration went prior to that because the erosion by that exposed to surface material which had been hydrated prior to that. In other case, when the water went on the surface of Mars, it was already too late for the water to remain stable. If you want to find a time during which water was stable, it's much earlier than that. And so, to be very brief, this is Mars Valles here. This is where we find the hydrated minerals here. And That's a 3D view of that. Again, there is no water essentially linked by hydrogen minerals here, but only on the margin here. And these are the cratered highlands made as hydrogen minerals much earlier than that. And you will see that's very important. So that's where Omega found these clays. So that's the summary of what I'm just saying. Sulfates and phyllosilicates are two different classes of minerals that require water, but they require entirely different environments. Acidic for one, alkaline for the other. And the question is that sufficient to build a new history? Can we, from that, say that Mars has given a history different from the one we have? And the answer is yes, for the following reasons. Minerals give access to what I call the enabling environments. It takes time to make a mineral, so in a mineral we can really know what that. And when we put the minerals in the context in which we see them, we can put a time direction there. And you will see that among time, the environment of Mars has varied. And essentially in this direction. The phyllosilicates form first, then the sulfates, then this anhydrous ferric oxide that I showed you. And there is no carbonate. And so there is a time arrow here, which is very important because these three sort of minerals really describe and characterize different eras that we have named as it's in here. Early in the process, we had conditions during which we could hydrate rocks into phyllosilicates. Then we have sulfates, and then we are up to now. This is now here. I have no time here, but the important thing that in between the two, Mars underwent what the Earth is experiencing nothing. We had a global change here. And as you will see, this is key because we consider that that's the time and the process by which Mars and the Earth had their pathway evolving in the diverging things. There are three things here which really took place there. The dynamo dropped somewhere here, the heavy bombardment sea somewhere in between here, and then you have the volcanic activity, importantly, that built the Tarsi things. Actually, the three have coupled. I have no time to explain to you why, but the process here are absolutely fundamental, I think, to understand why Mars and the Earth has diverging evolution pathways. Rapidly, in a minute, what we think is the following. To maintain the dynamo, you need a mantle convection very efficient. Mantle convection is the key here. And just because Mars is not sufficiently big, it could not maintain not only the mantle convection, but also the core convection, and then the dynamo itself. And when the dynamo dropped because of that, you didn't have a magnetic shield around to prevent Mars against the effect of the sun. And what has been underestimated is what the sun was at that time. What I've just summarized here is what is the sun today, and 4.5 billion years ago with three indexes, luminosity, the XUV emission, and the solar wind density. If you take one as a number now, the luminosity was much smaller at that time, so it was cold everywhere. It was very freezing everywhere here. If you want to be above the triple point of water on Mars, you need to have greenhouse effects and gases. But now if you take the XUV, you have hundreds more there, and it drops only by a factor of 2 or 3 in 500 million years. And for the solar wind density, about the same. You have 400 times more than now. In other words, the early sun, with respect to the atmosphere of the planets, was absolutely dramatic if you didn't have big shields. And this is why the existence of a dynamo to protect against the possibility for the sun to have an escape process is absolutely fundamental. And we consider that really what happened at Mars could not sustain a dynamo long enough to protect its own gases, and in particular the greenhouse gases, for water to remain liquid long enough for life to emerge. So the involved processes are very important. What happened afterwards is less important for the discussion I have now, so I go. So it's really our conviction that if ever life could arise on Mars, we have to find that prior to the global change that we have. At the time, the phyllosilicates formed, and that's where we have to go. We have to go to this era. If life started, we might find the relics there. The same, of course, for ExoMars 2 windows later in 13, if it happened to be there. And that's in preparation for Mars sample return. I really want to put an emphasis here to the fact that when you see the history of what we have among the past decades, 50 years ago, we didn't even know what interplanetary voyage would be. The lunar explorers, for the first time, allowed in-situ measurements to be made. And of course, as I said, it put this question of the emergence of life in the scientific era, finally. Viking, it was 30 years ago. Viking failed, and we know why. They couldn't land in the places where they had any chance to find any relics of that, because the place where they were were filled by water, by material without any water available at that time. We know why that's the case, and we know where we should go. So we really hope that in the next decade, that's where we will go. We are now in the position to say that after the coming mission, MSL and ExoMars, if they land where we are, we will know whether or not life started or not. Again, if it didn't start, at the same time, we have the reason to understand why Mars was, or the Earth was so specific, and the dynamo I talk about is one of the ingredients. Of course, it's not necessarily the same one. We really consider that if, by the end of the year, the post-ExoMars is decided at the MSR program, we might have in our labs, within the next, let's say, 2 decades, samples that will cover the first 1 billion years of Mars. And within these samples, we should be in a position to see whether or not we have biorelics still available there. If that's the case, I really consider that will be one of the most exciting adventures of the coming decades for the entire scientific community. It's absolutely remarkable that, thanks essentially to Mars Express, but not only, the European community plays an important and maybe critical role there. So I really consider that what happened among the past 4 years is fundamental with them. And I really strongly hope that the upcoming ministerial conference, which happened this November, will embrace that as really the goal to sort of justify the scientific venture of the next decades, because there is enormous things behind that. And I will finish thanking the organizer to have allowed us to present these few results here. Thank you very much.
Thank you very, very much, Jean-Pierre, for this wonderful excursion to Mars. Life or not life, it is alive. This is what he showed. Thank you very, very much.
Thank you.